Welcome to the Global Reader. Today, we enter the world of a woman whose work literally transformed our understanding of matter, Marie Curie. Her life was a relentless pursuit of knowledge, a journey that demanded immense intellectual fortitude and ultimately, the highest price of personal sacrifice. She shattered glass ceilings in science and society, becoming the first woman to win a Nobel Prize and the only person ever to win Nobel Prizes in two different sciences. This is a story of perseverance in the laboratory. Our English focus is on vocabulary for discovery and research. By studying words like hypothesis, experimentation, elucidate, and pioneering, you will acquire the precise and formal language needed to discuss scientific method, innovation, and intellectual breakthroughs. Listen closely as the flickering light of a radical new science illuminates her incredible life. Chapter 1. Driven by intellectual hunger, Maria Skłodowska was born in Warsaw, Poland, in 1867, during a time when the country was under Russian occupation. Though her family valued education, universities in Warsaw did not admit women. This systemic discrimination only fueled her ambition. To fund her dream of studying abroad, Maria made a pact with her older sister, Bronislawa. Maria would work as a governess to subsidize Bronislawa's medical studies in Paris, and then Bronislawa would return the favor. This early period was marked by quiet determination and personal austerity. In 1891, Maria finally arrived in Paris, enrolling at the Sorbonne under the French name Marie. She dedicated herself entirely to her academic pursuits, often enduring freezing cold and near starvation in her tiny attic apartment. Her primary focus was physics and mathematics, fields that required deep theoretical comprehension and rigorous analysis. She wasn't content to simply learn established facts. She was driven by the innate desire to ask complex questions and challenge existing paradigms. She successfully obtained degrees in both physics and mathematical sciences. Her brilliance soon attracted the attention of Marie Curie, an established French physicist who shared her inception for fundamental research. Their meeting was a perfect intellectual convergence, immediately forming the most important partnership in scientific history. Chapter 2. The pioneering hypothesis. Following their marriage in 1895, Marie was searching for a topic for her doctoral thesis. She became interested in the recent discovery by Henry Becquerel, who found that uranium salts emitted an invisible radiation similar to X-rays. Most scientists considered this a fluke or an anomaly, but Marie recognized a profound mystery. She formulated a bold hypothesis. The radiation was not a result of a chemical reaction, but was an intrinsic property of the atom itself. This was a radical idea that countered the then-accepted view that the atom wasn't divisible. She began her systematic experimentation in a makeshift, unheated shed at the School of Physics and Chemistry in Paris. The facility was far from ideal. It was damp in the summer and freezing in the winter, conditions that tested her physical and mental fortitude. Using a highly sensitive electrometer invented by Pierre and his brother, Marie began the long process of quantifying the radiation levels from various elements. She noticed that the mineral pitchblende was far more radioactive than pure uranium. This deviation from the expected result led to an extraordinary deduction. Pitchblende must contain an unknown element, far more potent than uranium itself. This was the pivotal moment of insight, the transition from mere observation to inspired conjecture. Pierre recognized the significance of her preliminary findings and immediately abandoned his own research on crystals to join her. Together, they embarked on the painstaking inquiry that would change science forever. Chapter 3. The arduous process of elucidation. The Curie's new objective was clear: isolate the unknown element from pitchblende. The challenge was the sheer scale of the operation. Pitchblende was a complex ore, and the unknown element was present in only trace amounts. To obtain even a fraction of a gram, they needed tons of the crude mineral. They obtained several tons of pitchblende residue, which had been discarded as waste, and began the brutal process of fractionation. For 4 long years, Marie worked under incredibly harsh conditions. She would boil down massive quantities of the ore in enormous vats, stirring the corrosive, boiling liquid with an iron rod almost as tall as herself. This chemical refinement was labor-intensive, exhausting, and physically draining. The work required meticulous attention, total and unrelenting perseverance. This commitment to the methodology was what set Theme apart. Her clothes were constantly stained, her hands raw, but she was driven by the belief that the tiny, invisible particles were waiting to Buneveld. In 1898, the couple successfully isolated two new elements. The first they named polonium, in honor of Marie's native Poland. The second, which possessed an unprecedented level of radiation, they called radium. They used the term radioactivity, a term Marie coined to elucidate the phenomenon they had uncovered. Their detailed documentation of their findings was published in multiple papers, establishing the new field of nuclear physics. Chapter 4, Eminent Recognition and Personal Cost. In 1903, the Curies, along with Henry Becquerel, were awarded the Nobel Prize in Physics for their joint research into the phenomenon of radioactivity. This accolade brought them international fame and funding opportunities, but the years of exposure to radiation had begun to take their toll. Marie and Pierre suffered from constant fatigue and illness, symptoms of radiation poisoning which they didn't fully understand. Despite the health concerns and the crushing poverty they had endured, the Curies made a profoundly ethical decision. They refused to patent their process for isolating radium. They believed that their discovery should be freely available to the global scientific community for the benefit of humanity. This act of intellectual altruism was a major sacrifice. Tragedy struck in 1906 when Pierre was killed in a street accident. Marie was left to mourn the loss of her partner, both in life and in science. Exhibiting incredible resilience and determination, she continued their work. She was given Pierre's professorship at the Sorbonne, becoming the first woman professor at the prestigious university. In 1911, Marie was awarded an unprecedented second Nobel Prize, this time in chemistry, in recognition of her work in isolating pure radium. She had become the only person to achieve such a distinction, cementing her unparalleled status as a scientific luminary. Chapter 5, The War Effort and Enduring Legacy. When World War I began in 1914, Marie Curie once again channeled her expertise towards saving lives. She recognized the immediate need for X-ray technology on the battlefield to treat wounded soldiers. She designed, equipped, and drove mobile X-ray units, which the soldiers quickly dubbed Petites Curies, Little Curies. She not only pioneered the technology but trained dozens of women to operate the equipment. This applied science had drastically improved battlefield medicine. She was tireless in this work, often working on the front lines herself, demonstrating extraordinary bravery and dedication. After the war, she continued her research, though her health was in constant decline due to long-term radiation exposure. She received great support from the American journalist Marie Meloni, who raised funds to purchase the necessary gram of radium for her research, a costly item due to the lack of a patent. Marie Curie died in 1934 from aplastic anemia, a direct consequence of her lifetime of work. Her notes and papers, even today, remain highly radioactive, stored in lead-lined boxes. Her life serves as a powerful testament to the pure, selfless pursuit of knowledge. Her pioneering work not only gave us the tools of nuclear physics, but provided the ethical paradigm for how great discovery should be treated not as personal property, but as a gift to the world.